So we're a couple lessons away from having all of our derivative rules down. And I mentioned before kind of what our list of derivatives is, the list that we're eventually going to complete. And so like I said, we're just about there. This second day of 3.8 is getting the inverse trig functions, inverse sine, inverse cosine, etc. And then when we get into 3.8, we will have the rest of the exponential functions besides just e to the x, as well as the logarithmic functions. So just 2 sections away from having all of the derivatives that we will ever need. And then at that point, we can take the derivative of any function ever, no matter how complicated. So we're going to come up with this list. We're going to do some triangle problems, kind of remember some of the inverse trig stuff, and then we'll get into our inverse trig derivatives. So remember, like I said, we need to recall these inverse functions, kind of remember what we're talking about. We did a little bit of these during our review, but just as a recap, first of all, in this example where I've got this listed, cosine inverse or arc cosine, they're the exact same thing. The book will use them interchangeably, and so I'm going to do my best to use them interchangeably so that you don't get used to seeing one and kind of forget what the other one means. We are going to use them both, just like your book will. So it is defined as the angle, because cosine inverse is always an angle. It is the angle with a cosine of x. Is the angle with a cosine of x. So, for example, if you wanted to find the cosine inverse of 1, for example, you're trying to figure out what angle has a cosine of 1. And the angle that has a cosine of 1, that falls within the restrictions, is 0. And that is the same as, that's what these back and forth arrows mean, that's the same as saying that the cosine of 0 is 1. So this is something that we know, or that we should know, depending on how well we know the unit circle, which I know for some of us is not very well. But if we know this, then this opposite statement is true, and that's because they're inverses of each other. The point 0, 1 is a point on the original cosine function, which means the point 1, 0 is a point on the inverse cosine function. One quick little note here that I've got on the bottom, very, very, very important to remember that that little superscript, it means inverse. It does not mean the reciprocal. Like x, the negative first, is 1 over x. That's the reciprocal. Cosine with that negative first, it's not the negative first power. It represents the inverse. Just like f to the negative first in function notation represents the inverse. All right, so let's look at some triangle problems. This is going to be the very first thing that we do. So if we remember this, those wonderful, beautiful cosine, or the triangle problems that we've done. So we start by trying to figure out exactly what this is. So remember, like I wrote on the front, sine inverse of x represents an angle. It represents the angle whose sine is x. So let's draw a picture for that. So draw a nice little right triangle. Here it is, right angle. So this angle will be theta, the one that we're talking about. So sine inverse of x, that's some angle theta. So let's write sine inverse of x equals theta, and that is the same as saying that the sine of theta equals x. So if the sine of theta equals x, remember sine is opposite over hypotenuse, so from this angle that means the opposite side is x, and then the hypotenuse would be 1. So we can do a little work with the Pythagorean theorem and then figure out what that missing leg is. So we can say that a squared, which we don't know, plus x squared equals 1 squared, which is 1. So to get a by itself, what we do is we subtract the x squared from both sides and then take the square root of both sides. And since we're talking about measurements, you would never even consider the possibility of the negative square root. So this missing piece right here, this leg is 1 minus x squared. All right, so that's where we're at so far. That represents all the sines based on this angle theta, based on the fact that we know that the sine of that angle theta is x. So then when we find the cosine of that angle, which remember we are writing as the cosine of sine inverse of x, the cosine of this angle is the adjacent over the hypotenuse. So that is the square root of 1 minus x squared, technically over 1. So that is the cosine of sine inverse. So what we're going to do is we are going to use this to find the derivative of sine inverse of x. All right, so we've got y equals sine inverse of x. We know that. And we want to find y prime, which is the derivative of this inverse function. However, we don't even know where to begin. We don't know what the derivative could possibly be. So what we're going to do is we are going to rewrite it in this notation, the notation that we're more comfortable with. So if we write it in original sine function, we flip the input with the output. So that means that the sine of y is equal to x. So now, even though our variables are kind of in different places from where we're used to seeing them, what we can do is we can take the entire function, the left-hand side of the function and the right-hand side of the function, and we can take the derivative with respect to x. So now this is implicit differentiation, which we just finished a couple lessons ago. So when we're taking the derivative of both sides, we take the derivative of sine y. This side is going to require implicit differentiation because I have a y as an input. So I start with the derivative rule. The derivative of sine is cosine. So I do cosine, I leave the y in place, and then the derivative of the nested function I write as dy by dx equals, and then the derivative of x with respect to x is just 1. So to get the dy by dx by itself, from here I divide both sides by cosine. Okay, and then what I'm going to write that as, so now this is my derivative. The derivative of this function right here is 1 over cosine y. You're like, okay, well, great. I don't want the y there. I would like things to be in terms of x because my function was once in terms of x. Well, what we do is we plug this back in. So going back over here, we're looking at cosine of y and wondering what on earth that means. We know we can make a substitution for y because we have it written over here that y equals sine inverse of x. So that is equal to 1 over cosine, and then again we're going to replace the y with sine inverse of x because of this relationship right here. And now if we backtrack just a little bit, we just evaluated this expression right here. We evaluated the cosine of sine inverse of x as this square root expression. So let's rewrite this one more time. So now this becomes 1 over, but instead of cosine of sine inverse, we are going to write 1 minus x squared underneath the square root. Just kind of copied that down. So this is the derivative of sine inverse of x. All right, so a little messy, but we made it there. So sine inverse, the derivative is 1 over the square root of 1 minus x squared. So if we were to do the same for cosine, for example, we would do y equals cosine inverse of x. We would write this as cosine y equals x. The derivative would be a negative sine y, dy by dx equals 1, all that stuff. So what ends up happening is this thing turns out to be almost identical, except that this derivative has a negative 1 over the square root of 1 minus x squared. And the reason being is because, remember in this step that I was talking about, since in this example this would say cosine, the derivative of cosine is a negative sign. So after the steps follow through, the negative remains. That's why this one is negative. So again, we mentioned that the other 5 can be proved in a very similar way. So we're not actually going to go through any of the proofs. I would be happy to show you any of them. Tangent inverse is 1 over x squared plus 1. And then remember, cotangent would give us a negative derivative. So in all of this mush, we would end up with a negative in the numerator. So these two are identical with the exception of the negative. And then secant is a fun one. We've got 1 over the absolute value of x and then times the square root of x squared minus 1. So if we're interested, let's see, I can kind of set up what the tangent one would look like really quick. See if I can do this quickly. So y equals tangent inverse of x. So if we were trying to get the derivative of this, we do the same first step that we did up here. So this is something that you could write down on a separate sheet if you're interested, because I know there are some people that really want to know where these formulas are coming from. If you are not one of those people, you can feel free to ignore this, skip ahead, whatever you want. So we're going to write this as the tangent of y equals x, and then we will take the derivative of both sides with respect to x. So when I take the derivative of this, I'm really doing a chain rule. So I'm writing secant squared of y and then times dy by dx equals 1. So when I divide both sides, here's where I'm at. Remember though, I don't want the y, I want tangent inverse of x. Oops, that's secant squared. So this piece in the denominator, I need to use a triangle rule to define that, which is exactly what I did up above. So if I do a quick little triangle setup, here's my right triangle, here's theta. If I know that the tangent is x, that means that the opposite over the adjacent gives me x. So I can find my third piece. So x squared plus 1 squared equals c squared. So that means that c is the square root of x squared plus 1. All right, so I'm actually, believe it or not, I'm just about there. I just need to know what the secant is. So the secant of that angle, which is the angle that has a tangent of 1, secant of that angle, secant is the reciprocal of cosine. So if the cosine is adjacent over hypotenuse, the secant would be the hypotenuse over the adjacent. So that would be the square root of x squared plus 1. So now the last thing, if I want to know what secant squared is, I take this term and square it, so I get x squared plus 1. So that is how this denominator becomes an x squared plus 1. That is where my first formula comes from. Whoops. So that this becomes x squared plus 1 based on all this right here. So that's the tangent formula. I can also do the secant formula very quickly. So y equals secant inverse. Again, this is just kind of supplementary. If you don't want to write it down, no need. You can even skip ahead. So I rewrite like that. And then I take the derivative of both sides. So the derivative of secant, and this is why this one's a little nasty, the derivative of secant is secant tangent. So I do secant tangent, but then times dy by dx. And then the derivative of x is just 1. So I divide both sides. So dy by dx is equal to 1 over secant tangent. But then I replace the y with secant inverse of x. Okay, so now this piece right here, in case you were wondering where on earth this absolute value term comes from, this is where. Secant inverse of secant x, what ends up happening, so say I plug something into my secant function, when I then plug it into a secant inverse function, I always come out with a positive angle. And so technically, no matter what angle I plugged in, when I take secant inverse, I always get something positive out, which is how I get that first part that has the absolute value of x. Because this term right here, the inverses almost cancel each other out, but like I said, it always comes out positive, so this ends up being the absolute value. And then this piece right here, I'm going to do one last triangle problem. So I'm going to set up the angle that has a secant of x. So secant is hypotenuse over adjacent. It's the reciprocal of cosine. So I am going to find this last little missing piece here. So I've got 1 squared plus b squared equals x squared. So I subtract 1 from both sides and then square root. So that missing side is the square root of x squared minus 1. So as the last little thing, I need to find the tangent of that angle. The tangent is opposite over adjacent, which is just 1. And so finally, I plug this thing back in, and that is where that comes from. Okay, so there are all your formulas. Very quick proofs. I know I went through them quickly. It was more just to see if you were interested in them at all. So that is where they all come from. Any of them, like this one, if I had done a cotangent here instead of a tangent, this derivative would be negative. So this would be negative, this would be negative. That's how it ends up negative. Same thing with this one. If I had done a cosecant, this would be negative cosecant cotangent. So this would be negative, this would be negative. That's how the overall derivative would end up negative. So they're all almost identical with the exception of the negatives. So last one here. So hopefully, I mean, whether you totally completely followed or not, or even if you hated it, hopefully you're able to see where these weird random algebraic derivatives come from. Like how I go from trig functions to having an algebraic derivative does seem kind of weird. So ways to remember them. These are all super cheesy, just hopefully something that will help you out. So all of the co-functions, cosine, cotangent, cosecant, so the co-functions are all negative versions. They're all the negative versions. That's one thing. Sine and secant. So this one and this one. So we're going to do a little bit of alliteration here. So sine and secant have square roots and subtraction. So you can remember your alliteration for this one. So sine and secant have square roots and subtraction, whereas tangent has neither. So the only thing you really have to remember on your own is that sine goes 1 minus x squared, secant goes x squared minus 1, but they both have square roots and subtraction. And the last one, this is the last or the best thing that I can provide you with here. Secant has the absolute value of x because secant sucks. I can't tell you why you'll use this or why you'll remember this, but you will. I have kids from years ago who the only thing they remember from this class is that secant sucks. So I don't know why, but like I said, it works. So we've got a few things to just kind of help jog your memory when you're trying to think of some of those derivatives. So some examples. We're going to find the following derivatives. Slight chain rule involved. So this one's arctangent. They were all listed in inverse notation here. Remember I told you that the book will use both, so I'm going to try to use both just to keep them fresh in your mind. So the main function is arctangent. So I start with my derivative rule. So good to kind of keep these in mind here. So y prime equals, so 1 over x squared plus 1, but instead of the x squared, I'm going to leave the x over 3 nested. So I just plug that x over 3 right into my tangent inverse derivative, but then because there's a slight chain rule required, I'm going to multiply by the correction factor, which is the derivative of x over 3. It's technically the same as 1/3 x, and so the derivative is 1/3. So let's clean that up a little bit, just because that, in my opinion, is very, very messy. So this, we've got 1 over x squared over 9 plus 1. And so this 1, we're going to do a 9 over 9, so we can get a common denominator in the denominator. And then times 1/3 equals 1 over, down in the denominator, we're going to have x squared plus 9 over 9, and then times 1 over 3. So when we're cleaning this up, this thing right here, I have 1 over an x squared plus 9 over 9. So instead of dividing by this thing, I can multiply by its reciprocal, which means I now have 9 over x squared plus 9, and then times 1/3. So the last thing to clean up is to simplify these down. So y prime ends up being 3 over x squared plus 9. And that is the most simplified version. All right, we've got a couple more of these to look through. Basically just some quick little chain rules within these rules here. So number 2, e to the cosine inverse of x. So my main function here is e, and we know the derivative of e is just e. So e to the, I leave my nested function in place, and then I multiply by the derivative of the nested function, which these are just something to memorize. The derivative of cosine inverse is -1, because I know that the co-functions are negative, and I know that sine and secant have square roots and subtraction. So just a little tip to remember. So let's just simplify up just a touch. So something like that. Okay, so that is your derivative for number 2. Number 3, I have cosecant inverse of x to the negative first. So when I combine all these, so my main function is cosecant. So actually this isn't equal, y prime equals the derivative of cosecant. It is a co-function, so it has a -1. Secant has the absolute value of x because secant sucks, and secant has square roots and subtraction. So all lots of little things to help you remember that. Now, we need to remember that we've got our x to the negative first. So this becomes negative 1 over, instead of just x, I have x to the negative first. And then the square root of this becomes x to the negative second minus 1 underneath there. All right, so let's clean some things up a little bit. I'm sorry, and then the last thing is that I multiply by the derivative of my nested function, which is a negative 1x to the negative second. Okay, so lots of little algebraic things that we can clean up here, and I know many of you don't want to, but I told you I'm an algebra person, so I'm going to do it. So we've got a negative 1 times a negative 1. Those two things are going to cancel each other out, so I'll be left with a positive 1. So positive 1 over, lots of things going on here. That x to the negative second means I now have an x squared in the denominator. The absolute value of x to the negative first means I have the absolute value of 1 over x. This piece right here, underneath my square root, I actually have a 1 over x squared minus 1. Okay, so lots of things to simplify. So 1 over, take a look at these denominators here. This I'm going to multiply by an x squared over x squared so I can get a common denominator. So I'm still cleaning things up a little bit. So x squared in the denominator, and then the absolute value of 1 over x, square root of, here's what I've got. This is going to be a 1 minus x squared over x squared. Okay, so just a little bit more simplifying to go. So 1 over, here I have my x squared, here I have the absolute value of 1 over x. So now these two things I can split up. I have the square root of 1 minus x squared, and then over, remember when I take the square root of x squared, it actually comes out to be the absolute value of x. That's something that I'm hoping that we remember from our review chapter. So the last little thing that I can do, I have the absolute value of 1 over x, and then here in my denominator, I have the absolute value of x. So what I really have is I have an x times x in the denominator. That's an x squared. That's going to cancel with the x squared that I have right here. So again, these two pieces, I technically had a 1 over x squared, which canceled out with this x squared. So what I have is 1 over the square root of 1 minus x squared. Now here's something interesting to point out. You probably recognize this, even though we've only been doing these for a few minutes. That is the derivative of inverse sine. Here's what I did. I took the cosecant, which is the reciprocal of sine, of the reciprocal of x. So the reciprocal of sine of the reciprocal of x lands me right back at the sine inverse. So, little fun fact. That'll happen in the future if you try to do it again with any other inverses. So my last one of these examples right here, another chain rule. So my original function is cosine, cosine inverse. My main function is cosine inverse. So I start by taking its derivative. So y prime equals, so cofunctions have negative derivatives. And then sine has square roots and subtraction. So I do 1 minus x squared, but I'm going to leave this beautiful quantity right here. And then times the derivative of the nested function. So the derivative of this thing that I have in parentheses, the derivative of x is 1 plus, and then the derivative of sine inverse is 1 over the square root of 1 minus x squared. Now, lucky for you guys, there really isn't a ton that I could do here, or I guess a ton that I want to do. So what we're actually going to do, and I'm sure that you are fine with this, is we are just going to leave it the way it is. So that, not very much that we can do to simplify. All right, last little thing here. This one's really, really quick and easy. This is something that could appear on a multiple choice section. 28 would be a non-calculator on the multiple choice section. So when we take the derivative of this, y prime equals the derivative of the main function. I've got 1 over the square root of 1 minus x squared, but of course I'm going to plug in a 5x instead of an x. And then I multiply by the derivative of my nested function. My nested function is a 5x, so its derivative is a 5. So none of these really appear to match with this right now. Since it's multiple choice, we can talk about the process of elimination. This is not what a sine inverse derivative looks like at all, so those two are out. And then if we're looking at these three, really anything is fair game. Take a look at C, though. I know my derivative is not going to be negative. So if we cancel this out, now let's take a look at what I'm going to get. So I have a 5 in the numerator over square root of 1 minus, this ends up being a 25x squared. So both of these have that 1 minus 25x squared. This one has a 5, which is the correction factor. So this would be a very sneaky one if you forgot your correction factor. So this is letter E. All right, so I believe that that is it. Yep, that is it. We're getting there, guys.